Okay, so for now, definitely welcome to today's lecture. We will stop at 3:45 as usual. Yeah, I didn't think that, I thought that because I stopped yesterday 5 minutes earlier, today I compensate by starting 17 minutes late. Yeah, but okay, my apologies. I gave another course, and I looked at the watch and said, "Oh, it's 20 to 1, so I have 20 minutes to continue until 1." But I should have stopped at 1:15. Yeah, and the students didn't say anything. Yeah, very young, obedient. Yeah, so please tell me when I'm 15 minutes over time. Yeah, even earlier. So. Okay, so we have seen yesterday, interestingly, that actually, we can calculate the effect of the Lorentz force on the carrier motion, and in the form of an expression that relates the current density with magnetic field to the current density before the magnetic field was switched on, without magnetic field. And I can even write this as sigma n0 E, as I just insinuated, and of course everywhere else, sigma n0 E, and the same here. Yeah, and then thereby I will relate the current density to the driving electric field that drives that current density. And what we have seen is that actually, in case B is not pointing in the direction of J, for instance, perpendicularly, then we have a term of the current density that goes perpendicularly to both the original J direction and the B direction. So the Lorentz force somehow deviates the current density from the originally intended or prescribed, the direction prescribed by the electric field. And then there is this other term that is quadratic in B, but then there's also a term with quadratic contributions in B below this expression, which somehow attenuates this expression. And you see that everywhere where B appears, it always appears in conjunction with mu. So this is the quantifier for the strength of an effect. You will find mu B all over the place. Yeah? And this is true, this expression, or this general expression is true for semiconductors in particular, but also more broadly for metals, under the assumption that all carriers have the same velocity. Yeah? Why do I say that? Because I said, okay, we have a velocity v, and that velocity v is given by the electric field in the form of a current being driven and so on. So there are many expressions that I wrote down last time, and now that velocity v is deviated into another direction, because j and v are of course intimately related. And so j is nothing else than the charge is moving with the velocity in the direction. And so this assumption that all carriers have the same velocity is not really true. And so very generally, one could write that actually in this, so now this is more fundamental semiconductor theory. Some of you have heard my semiconductor lecture, so actually 2 of you know, the others haven't had that lecture, but you may have seen elsewhere that, for instance, in silicon, if we draw the reciprocal space, the K space that is used to designate the wave functions, Kx, Ky, Kz, then in an area called the first Brillouin zone, we can define some points, and the electrons are actually sitting in K space near those points, in pockets that have this ellipsoidal shape, the symmetry of those points, so different in the longitudinal direction from the transverse direction and two identical transverse directions. And so there are these 6 electron pockets, and so these states where the electron resides are close to these points, and the energy, so these points correspond actually in energy to the conduction band edge. So correspond, I should say. It's not equal to, but they correspond to the conduction band edge, and the farther away you are, the higher the energy parabolically, in this ellipsoidal way. And then you can associate with each carrier also a velocity, and that's given by the derivative of the band structure with respect to k. So every carrier has its own velocity in these occupied states. Every carrier in these occupied states has its own velocity depending on where its k is. And then those states are occupied with a probability function, the Fermi function, that dies out the higher you are in energy. Therefore, the farther away you are from these EC points, the less occupied the possible states become, and that allows us to draw these ellipsoidal shapes and say this is where the electron sits. So, and then there is another thing that actually those electrons, okay, they move with their velocity, but they collide with their environment after a time. And they do so for 2 reasons. First, they can collide with impurities in the semiconductor. The dopants are impurities, and the more impurities there are, the higher the semiconductors go, the more strongly they collide, the less longly they can propagate uninhibited. So there is a relaxation time, tau, that one associates with each state, tau of k, that says how long, on average, a carrier with k specifying its wave function can travel without collision. And so one reason was this impurity scattering. The other one is the lattice scattering. Lattice scattering is caused by the motion of the silicon lattice, the motion of the silicon atoms in thermal vibrational motion. Those atoms vibrate, and this imperfect crystal is also an inhibitor against free motion of the electrons. And both have different thermal behaviors. Yeah, so there's a question there. Yeah. And you have to look this up in this is not a semiconductor course, fundamental course, so please look up band structure of semiconductor, yes, and then you will see that, or electron states in semiconductors, and you will see that. And so then we also have actually, so this is the most general way of stating it, and then people say, okay, actually, let's consider that actually electrons with higher energy collide differently from those with lower energy, and there is a certain relationship that, rather than depending on k, is postulated to depend on E. So you can imagine that electrons who sit here in states at the bottom, they have actually velocity 0, or low, near those points means low velocity. If such a low velocity electron moves and it feels, for instance, it feels the influence of impurities much more than a high velocity electron. You can imagine that an impurity is a charged body. It has one more, for instance, a phosphorus atom, phosphorus dopant has one more nucleic charge than electrons surrounding it. It got rid of one of its electrons, so it's not neutral. And this charged center will influence the motion of a low velocity, low energy electron more strongly than one that can pass by very rapidly, essentially uninhibited. So there is an energy dependence on this relaxation time, and these I mean, there are theories subjacent to that due to Herring and others that state that. Yeah, Herring is the physicist at Bell Labs who developed those theories for the first time, and so now you can, if I draw this, this is only qualitative. Yeah, I don't carry out the calculation. The calculation is actually quite intricate. Yeah? And if you would like to see the detail, you can, or some form of the detail, you can look up a book by Popovic, Radivoje Popovic, Popovic, which no, there's one po too much. Popovic, yeah. So it's called Hall effect devices, I think. Isn't that correct, Anya? Hall effect devices. It's not Hall sensors or something. Hall effect devices, and there are two editions. The second edition is a bit more complete. Yeah. Yeah. There's another question. Yes. It's not electric. It's energy. Yes. Don't strangle because of this energy. Yes, this is energy. Just like E here is energy at the conduction band, and here we have an energy scale, and you know that, or you may have seen in my or other lectures, that there is a density of states, D of E, that has this parabolic or square root shape. So square root of E minus EC in this uppercase, and square root of EV minus E in the lowercase. And then the Fermi function lets actually these available states, whose number is specified by D of E, be occupied in a way that somehow dies out exponentially, like this. So for instance, I'm drawing here a clearly n-doped sample with more n's than p's. Yeah, so this would be p, and so more electrons than holes, and each of those electrons has a tau that depends on the energy, on that energy scale. And when you fudge this whole thing up in the correct way, which is intricate, believe me, then you reach the conclusion that the equation that I wrote before, namely this one, is not completely correct. And how to deal with this is by introducing some correction factors. Fortunately, those correction factors are not gigantic, so it's not all wrong. What I wrote so far is just slightly wrong. So for instance, in this earlier equation, we had mu n here. Now let me write that in black. We had mu n, the mobility of the electrons here, same here and here, mu n, and we didn't have any k in there, and now mu n is replaced by mu h, and then there is this additional k, so here same, mu n. So mu h is called the Hall mobility, therefore it's index h, and this is equal to a correction factor times the mobility we used before. And that correction factor is not gigantic. Here you have some values, 1.18, 1.93. I think I copied them out of Popovic's book many years ago. So in case phonon scattering, the lattice scattering dominates, then it's clear that the higher the temperature, the more strongly the scattering occurs. And this, together with the thermodynamic distribution here, and a tau of E that one can compute for this type of scattering, leads to an RH of 1.18. And if impurity scattering dominates, so the dopants dominate, which means that the temperature is probably not too high, or the doping is high enough, then this tends, or this can be 1.93. But you find lots of values, also experimental values, and we have also tried to measure that by correlating the Hall response and the conduction response, and we found rather something close to 1. And we did not go into detail why this is so. Yeah, but anyway, it's a correction factor of the order of 1, which is good news. The correction is not super significant. And you can implement it here. Yeah, once you did that, you still have this second effect, and that these thermodynamic averages turn out to be slightly more complicated, involve higher order terms, and then there's a second correction factor that needs to be added, a k, which is also of the order of the magnitude of 1. So it's not exactly 1, it's somehow 1, or whatever, 2 or 0.5. I don't know. So because we rarely deal with the second order effects, not knowing that k actually is not so important. If we were dealing with high mobility semiconductors in high fields, then the nonlinear effects would be strongly pronounced, and then we would have to think about it more closely. But this is a CMOS technology, which means mostly silicon technology cores or sensor cores, and therefore K doesn't need to be specified so exactly. So just so that you know how this comes about. So for instance, for RH, one has to compute some averages. So this means average tau square. And average in what sense? Well, tau is a function of E, and then you average something over the Fermi function, which under the circumstances is some E to the E over KBT, something like this, dE, and then this would be, for instance, an average of tau. So with a normalization constant. So I should write here Cn for normalization constant in front, so that this is all correct. And if we did tau square, then we would have to elevate this to the second power. If we write tau to the square, it means the expression without the square squared. So it's clear that this is not 1. If you have a distribution and square what you integrate and take the simple average and then square, this is not the same. So that's why these RH factors are not equal to 1. So I don't want to go much into more detail here, except that KH, and I should be correct. I should write KH here. And the second Hall correction factor, and N might indicate that we are still dealing with electrons, as we have been all the way down to here. It contains other such averages with the third power of T under the integral. So that's just some background knowledge without any examination relevance. So when are these expressions valid? First of all, when there is no temperature gradient. So isothermal, that means the temperature is the same everywhere. It can be varied, can be various temperatures, but in the sample, it's always this temperature, increasing everywhere. And then, of course, we have N of T, we have mu H of T. Many things can depend on T. Even the correction factors might depend on T, because it's not so clear whether it's only impurity or only lattice scattering. So that is all possible. And then under these conditions, that only these galvanomagnetics and not galvanomagnetic effects are considered, then we have this general relationship between J, E, and B that we basically have already seen before, 3 slides ago, when we can extract the sigma 0 everywhere. And then we have E instead of J0. This is what you have here. And we have these additional correction factors implemented. So this is the general equation, and the sigma NB is sigma 0 divided by 1 plus mu HB squared in this approximation. So what are the conclusions? Well, first of all, if you would like to have the strongest possible galvanomagnetic effect, the strongest Hall effect, then clearly mu h should be maximized. For a given B, making mu h larger makes this effect larger in comparison with what you have without the B field. And so that is the reason why one takes N silicon rather than P silicon, because mu N is about 3 times as large as mu P, and therefore mu H of electrons is about a factor of 3 larger than mu H of holes. And then if you take that conclusion further, you would say, well, then let's at least take a semiconductor with a higher mobility than silicon. Why not taking gallium arsenide or indium phosphide with really large electron mobilities? Now, then we would have a super duper Hall sensor. And the professor can only say, yes, you could. Yeah. But then, yeah, who can produce that sensor in large masses? Yeah. Is there CMOS technology available in gallium arsenide and indium phosphide to have some circuitry to do all the nice things that we can do in silicon? Then it gets trickier. Yeah? So for specialization sensors, these other 3-5 semiconductor sensors are fine, and there are research publications also coming out, possibly even some commercial products. Yeah? But silicon prevails, at least in the mass market. Yeah? And then also it is good to know that mu HB is kind of the size quantifier here. So once we have mu H given, then we can decide how large we can go in B in order for the theory to be simple, and when we should start worrying about the theory no longer being simple. If mu HB is much smaller than 1, significantly smaller than 1, then essentially the effect is linear. Otherwise, it's nonlinear. So what does significantly smaller than 1 mean? So if I write here, well, they equal to 0.1, 0.01, and so on. Where would you draw the limit? What would you say? Gut's feeling. 0.01 is definitely very much smaller. Yeah, and then the other terms that are also appearing with the square would be of the order of 10 to the minus 4. So the original current is, or the first term is size 1. The linear term is size 0.01, 1%. And then the nonlinear thing is yet a factor of 100 smaller. Yeah? Okay, that is for sure the case. And how large can B be for mu HB to be 0.01? Let's see, mu HB is equal to 0.01 would mean that B is equal to 0.01 divided by the mobility in the same units as B. Let's say we want B in Tesla. Then we need to express that in Tesla. And I know that for low dope silicon, as I mentioned before, the mobility in N silicon is 0.145 or so, 14. I think I mentioned 0.14 yesterday. Yeah, so that's maybe already too much precision for this consideration. And so this is 0.07 Tesla, approximately. Is that correct? I'm dividing this by about 10, which moves this one up by, I'm dividing by more than 10. So it moves this down. So yeah, so 70 millitesla, okay? For B fields below 70 millitesla, we are on the safe side. Yeah? And I tell you, well, even with 0.1, we're still pretty much on the safe side. Okay, then we have an effect that is 10% of the original thing, and then the disturbing second order effect is 1% of the original thing. Well, but we make still an error of 10% between the linear and the second order. Okay, so somewhere in between here may be tolerable. 0.01 is probably a bit on the very safe side, but it's definitely on the safe side. And it gives access to many magnetic fields. If you have a, producing 70 millitesla is not so easy. If you wind a coil with millimeter copper wire, 100 loops, and then you send a current through, let's say an ampere or 10 ampere, the thing gets warm, so you can't go much further, and you measure the field near this coil, you'll have a few 10 millitesla. So to produce Tesla is really not easy, except if you have materials that have that, but by electromagnets, it's not easy to do. You need huge currents in hopefully superconducting wires that let you run those huge currents through the material. Therefore, you need to cool down for the thing to be superconducting, and therefore you have these big machines. So when B is parallel to E, when B is parallel to E, it means that this cross product is 0 and only this survives. What does it mean? Then J for that E and that B is equal to sigma NB, which is, well, sigma N0 divided by 1 sigma N0 divided by 1 plus sigma 1 plus mu HB square. So has this quadratic term, and so does the denominator. And imagine now that K is 1. Then you have up here 1, and then you have mu HB again, the same. You can extract E. So this looks like sigma NB times 1 plus mu HB square times E, and then this gets divided thanks to this term by the same denominator. And so in the case of K equals 1, in the case of we have JEB equals sigma N0 times E. So if in this simple conductor with only one kind of carriers with same velocity, all carriers walking in unison under the electric field through this conductor, same velocity, then the magnetic field going in the same direction as this conductor does not feel the magnetic field. It's not amazing, because I mean, if those conductors, those electrons go in this direction and the magnetic field shows in the same direction, there is not even a Lorentz force. Nothing. So we understand that as well. There's no angle between B and V. Things get interesting when B is perpendicular to E. That means that B dot E is 0, which means that only the first correction term remains. And this can then be written as, and actually here, honestly speaking, we can also replace the sigma NB by sigma N0, because we are now considering in the denominator only linear effects. Well, actually, we cannot generally replace it here, so let me put that between brackets, because if we have perpendicular field for large enough field values, the denominator of sigma NB will play a role. It will decrease the sensitivity, but for small enough fields, of course, this is what we have, and then this can be replaced. So in approximate or equivalently, this can be written as the original electric field that is applied to drive the current, plus something which is perpendicular to the original field. And I'll just write E trans here. So it looks like the current is driven by an electric field that goes in the direction of the original field. And then there is a second field, a resulting field, magnetically resulting field, E trans, that also drives the current into this sideways direction. This transversal galvanomagnetic field perpendicular to E and B. And this is represented here in this graphic, where we see, so we have this volume, conducting volume, and then it is pervaded by an electric field E pointing in this direction. And then there is perpendicularly to it a B applied. And then, of course, there is a mu HB cross E. Well, mu HB cross E, B cross E makes a vector going in this direction, which has a certain size, and it has the units of electric field, because mu H and B have inverse units. So this is like a number one vector or a unitless vector, and therefore this is like an electric field. And the sum of those two electric fields, here is where the current goes. So this is the current E and B. So there is an angle between the current density and the original driving electric field. And that angle is called the Hall angle, theta H. And it's easy to see that the tangent of this theta H is equal to the transverse by the longitudinal component. And this is equal to mu HB, because B is perpendicularly to E. And you can even, for small B fields, you can even say that the Hall angle is asymptotically equal to mu HB, because the tangent goes towards one, or towards its argument for small arguments. Tangent of X goes to X for X going to small. So this is interesting. We would like the current to flow in a direction, and the B field makes it flow in another direction. But it's not only interesting, it's very useful. Now imagine what happens when J is forced into a direction. Assume a large strip of material, and you drive a current through an electric field, and the current can only flow along that conductor. What does it mean for the electric field? I mean, there must be an angle between the two. I'm drawing this long conductor here. And I'm applying, however, a current density through this current, and it is forced by the boundaries of the conductor. It cannot flow in this direction. I apply an electric field in this original direction, E, without B. J goes in this same direction, no doubt. And now I switch on a B perpendicularly to that conductor. And then the current cannot now rotate out of the direction with a Hall angle theta H, because that would mean that there is a current contribution disappearing from the conductor. Where? There is conducting material only in this middle, and outside it's isolated. So the current must flow there, and as a result, the electric field must be rotated by the Hall angle. And there is nothing bad about that, because the electric field can flow wherever it wants. There is no boundary against the electric field. There is no infinity conducting material, something that does something to the electric field. There's free space up there. Material space. So the current and the electric field are related by, so this is the real one, and this is real. Yeah, and then there is this theta Hall in the same relationship as you have seen it down here. And it means that the electric field still has this component, horizontal component. We are still able to apply a voltage difference, setting up this horizontal component of E. But then in addition to that, a transverse electric field is also appearing. And that transverse field causes a voltage difference between top and down, or top and down between this boundary and this boundary, so that when I make a measurement in this direction between two such points, between contacts at these outer boundaries opposite to each other, I will sense this electric field as a voltage difference, because electric field integrated over path makes a voltage difference. Well, this is the secret of the so-called long Hall plate. The long Hall plate is a conductor that is significantly longer than it is wide. It can have contacts that are extended on the sides. And then the resulting flow lines in this conductor, at least in the middle section, sufficiently far away from these distant contacts, is horizontal. There is this horizontal flow, flux density J, whose direction is prescribed by the geometry of the device. And then the electric field in that region is oblique, and therefore the potential, the equipotential lines, equipotential lines that are perpendicular to the electric field, because the electric field is equal to minus gradient of the potential. Let's call it U or phi or V, or all those symbols that are used for the electrostatic potential. Those equipotential lines are these lines. They're perpendicular to the electric field, and they're oblique. So that now between contact 1 and contact 2, very evidently you see that those contacts sit on two different equipotential lines. That's the Hall voltage between those contacts. And the obliqueness of those lines is the same obliqueness, those obliqueness with respect to this direction here, is the same Hall angle, theta Hall, that is also the obliqueness of E with respect to J. So verticalities, perpendicularities are built into this construction. And so the Hall angle also prescribes how much voltage we will get out. And if the Hall angle is 0, then the two contacts sit at the same potential. And the stronger B becomes, the stronger the difference is between the potential. If the B gets negative, then the obliqueness goes in the other direction. And then you get another sign of your Hall thing. So this simulation was done, it's a very long time ago. I think it was done by Rocky and Nathan, in the 90s or so, just to illustrate a book chapter, which, and it was done at 0.21, which is quite strong. I mean, mu h times b equals to 0.21 means 1.5 Tesla or so. So it's for an imaginary magnetic field, not unrealistic, but it's mainly designed to bring out the effect graphically. If I had a small field, millitesla, we wouldn't see anything in terms of obliqueness. Although electrically we would be able to measure something. So that is this. Now we can analyze this Hall plate in more detail. So that means we will analyze this equation here, and actually for the purpose of the analysis, I also set this to small b values, sigma and 0. Okay. So if I write this vector equation in terms of components, yeah, then my Jx is equal to sigma n, and let me correct that here or simplify that here, to sigma n0 times Ex plus the X component of this cross product, and the X component of this cross product for E lying in the, so B is in the Z direction. Yeah, so B is 0, 0, BZ. I should say that. And then E is in the XY plane, EX, EY, and not in the Z plane. So there is a flat conductor, and then we have this flat conductor crossed by the magnetic field. And now we look at whether we can make any quantitative sense out of that device. And so we have here the sigma times Ex, and then the X component of B cross E, that's EY times BZ with a minus, yeah, and then times the mu H, the prefactor here. And then JY, analogously, it's EY times sigma n, and then we have here plus mu H BZ times EX. So how EX and EY and EX and EY are mixed in these two current components. And so in the middle section of the Hall plate, what do we have? We have definitely J in the Y direction is 0. So let me put some axes on this Hall plate. This is the X axis, and this is the Y axis. And then we have perpendicularly, here is the scale. Perpendicularly, we have the Z axis. X, Y, Z. The natural Z axis would come out of the plane, yeah, to be a right, correctly ordered coordinate system. Yeah? And so JY is 0, and that means that the second term is 0. That means that this is 0, which implies this equation here. EZ minus, yes. Okay. And then what can I remember? Let me just check my own slides here, whether I'm doing that correctly. So I can just have my Spickzettel. So if I write EX as 1 over, so actually as sigma n0 times Jx, so in approximation, un, so without B field, that's what I would have. Then I can insert this result in here and substitute a little bit and replace the Ex by Jx. And then we have here, well, an expression that actually, once I substituted it, looks like minus mu H over mu N times 1 over NQ, and then Jx BZ or BZ Jx to keep the order in which you have it here. And this coefficient here, this is called, is written RH, and is called the Hall coefficient, R. This has nothing to do with the resistor. R is not always a resistor, and here it doesn't have at all the units of ohm. You can calculate what the units are. It's 1 over the units of N times Q. So there is 1 over charge, Coulomb second, Coulomb, and then per Q. So it's cubic centimeter per Coulomb. That's something. So not a resistor. So this R, it's kind of a quantifier of the effect. How much field, perpendicular field will we get? Because that is the message here. We have a current in the X direction, and we get a field perpendicular to that X direction, the original direction. And that quantifier is this Hall coefficient, which I personally find usually rather well, a bit confusing, because well, you can remember it rather fast, but you know, what does it mean at the end? Yeah, so mu h over mu n can be written as RH. That is the relationship between the two, and then you have divided by Qn. So this is also this result here. And now, once we have this this long conductor, this field EY, due to the current flowing in the x direction, then we can just determine the voltage difference between these two contacts. And that voltage difference V2 minus V1, so let me be sure that I have the same numbers here. So here with 1 and 2, so voltage at 1 minus the voltage at 2, that's E times the width of that plate. Electric field times length for a homogeneous electric field is equal to the voltage difference. And then we can insert for EY the result we just had. So RH times JXBZ times W, or we can write that again in a more complicated way by multiplying this with T, and then dividing it also by T. What is T? T is the thickness of the plate. And then WT is the cross-sectional area, A, so to speak. And then we multiply, obviously, JX by the cross-sectional area, and that becomes the current, the real current in ampere. But then we have this additional T. So you can write this again as, then I need some separate slides. Let me see if I have one. No, I don't have it here. Open recent, Halbleiter, empty pages. We have here. Yeah, we have something here. Yeah. Okay, so let me just write down here. So for instance, so we start from RHIN. So this is the Hall voltage. Now an important result. RH times IN times B Z. And then why don't I divide RH by T? This used to be minus RH for electrons over NQ, and now I have this additional T in there. So when you look at this, how can we interpret this? This is like a charge density, volume charge density times the thickness. That's a sheet density of charges times Q. That's the sheet charge density. How many Coulomb per square meter there are in this conducting layer? So the electrons, how many coulombs do they represent per square meter of area? It's kind of a sheet charge density. Well, for those who can make use of that. You can also write it differently. I can write this as RH over NQT. And then instead of having IN, why don't I write VN, VIN? What is that? IN, the input current. I could write that as the input voltage divided by the resistance of that thing. Let's call it Rin. Times BZ. And what is Rin? Rin is rho, the resistivity, times the length of the device divided by the cross section, WT. What is rho? Rho is 1 over conductivity. It's 1 over sigma, and which is 1 over Q and mu, times L over WT. So if I insert that up here, we end up with RH over Q and T. And then we have V in the back. We have VZ in the back and something in between, namely 1 over Rn. And that's, did I do something wrong here? Yes. So because Rin is in the denominator, this is switched over. And so we have Q and mu in the numerator, and we have WT also in the numerator. We have L in the denominator, and then we can cross out quite a few things, namely QN, yeah. Then we have T gone, and what remains mu and W. Okay, so this is equal to RH times mu n. Oh, that's mu Hall, yeah, times W over L times V in times PZ. Yeah. Another way of writing the response coming out of this Hall center. So either you imagine this Hall center to be a device into which you feed in a current, 1 milliamp, and then if you know RH and T, you can compute how much Hall voltage for a given VZ you will get out. Or you imagine this to be part of a system that drives it with a voltage, an input voltage. And then if you know the Hall mobility of the carriers and the geometry, you will also get out the Hall voltage. So what, depending on how you drive the system, if you look at the system a little bit differently. So if you say, oh, my I in is given, and I can change all the other parameters, what will I do to obtain a super duper Hall voltage? The conclusion would be that you will make this factor as large as possible. That means that you will make, for instance, the conductor as thin as possible, T as small as possible, that you will make it as low doped as possible. What else can you do? Nothing. You drive this current through this thin, low doped sample material. And then you will get a large Hall voltage. But that thin, low doped sample has a high resistance. So in order to drive this current through the device, you need a large voltage. Okay, so it looks like for your current, you get a lot of signal, but you need to have a large effort. And therefore, other people say, well, I'm limited in voltage. My circuitry can deliver only 3 volts maximum. V in is a limiting factor. Not my I is given, the V is given. And then what can I do to make this device as good as possible? Well, I can make the Hall mobility as large as possible. Now that's what it means, which also means doping, low doping if possible. And then I can maybe work on this geometry factor. So let's call this a geometry factor related to the voltage response. I can work on the geometry. That's the conclusion. And now, of course, the next question, how do I make an optimal geometry? We'll have to see that. And before doing that, let us look at some of the sensitivities that can now be derived from what I just said. So you can ask, how much voltage can I get out of this device per magnetic field? If no matter what I and V in are, if your figure of merit is just voltage out per magnetic field, then based on what we just saw, this is RH times I in divided by T. And the units of this SA, this absolute sensitivity, is volt per Tesla, like written here. So it's easy to make a large SA value. So if your sensor is crappy and you would like to post a big number in your publication, you just say my sensors absolute sensitivity is so and so many volts per Tesla, but you're driving it with a really large current. RH times large current, i.e. makes a large SA. Yeah? And the not so naive readers will ask, well, at what current did you drive it? You know? Okay, so you're not much better than the rest of the world. Yeah? So yeah, I mean, I stumble across such things in conferences, and people boast the figures of merit that suits their purpose best. Yeah? Question, you know, but yeah, isn't it that? You know, when we compare that, you know, if they drove the device with the same things, then what? Yeah, then another sensitivity is the current-related sensitivity, SI, yeah, which is a more refined way of stating it. It's the output voltage per magnetic field per current that you drive in. Yeah? So it's the absolute sensitivity SA divided by input current. I could also write that here. This is absolute sensitivity divided by IN. So a more objective parameter. And that can be calculated. It's Rn, or let's call it RH to be consistent with the previous. Oh, now I can't see it anymore. Yeah, so this is all green. Yeah, so let's call it RH, the Hall correction factor divided by Q and T. Yeah. And yeah, if that is the parameter that suits the author of the journal best, he will quote SI maybe rather than SV. Yeah? But anyway, we have to remain on the ground of on the safe ground of reason, and so this VH, this absolute sensitivity may not be you know, the best number. But anyway, if SI is given, yeah, that is fine. You can multiply it by the B and by IN to know what your output voltage will be. So it's a useful number. Yeah, you just have to know at which current you drive the device. Yeah? And the units are V over AT. Yeah? V over ampere and Tesla. V over volt over ampere and Tesla. Yes. Yeah, it cannot be. You need to remove this here. Thank you. Well observed. Cannot be. Have to divide by IN. Yeah. Right. And then we have the third. Actually, the third sensitivity, which I like actually the most, because I know that the voltages with which these sensors are driven are bounded by circuitry. And so this is a voltage related sensitivity, which is given by the output voltage per input voltage per magnetic field applied. So once you have this SV, of course, you can again calculate the Hall signal from SV given a B, given an input voltage, 3 volts or 5 volts or 1 volt. Yeah? And it's easy to see that actually, so this is for the long Hall plate. So I should write here for the long Hall plate. This is mu H times W over L. In very general terms, this is mu H times some number reflecting the geometry. Not necessarily the width over the length, but some geometry parameter that catches the whole geometry in one single calibration factor, GV. And so in this case, to make SV largest, you have the option to maximize this or to maximize that, or both. And the unit of SV is volt per Tesla, or per Tesla, or percent per Tesla. These are the units that you find in the literature. Now, so let's look at optimizations. So it is clear that optimizations of SI, and I'll no longer talk about the absolute sensitivity. SI and optimization with respect to SI and SV will be totally different. So in the SI case, the long Hall plate is actually good. So what does it mean? You have this long Hall plate, and these rugged lines on the left mean just that the conductor continues here on the left. And we don't know where the contacts are. They're somewhere out there on the left and the right, and we just see a section of this, and the current density is constant or homogeneous in this plate, and then the sensitivity that comes out is RH divided by Q and T. As soon as you make this long plate shorter and shorter, you will be worse and worse. So the sensitivity will no longer be SI, but it's going to be this prefactor multiplied by a geometry factor that we could call GI. And then, so for instance, for a plate that is only that long, with contacts right here, somehow the proximity of the contacts has an effect. And it's quite easy to see why that is the case. Because imagine these contacts to be closer and closer. For the Hall voltage to appear between the two side contacts, the voltage needs to be able to take this inclined shape. But the contacts are highly conductive regions. They are equipotential lines. They are at 0 volt and, for instance, 1 volt to drive a current through. They're equipotential lines, and those equipotential lines are vertical. And so, as the current flows, given enough distance to the contact, it can take up, or it can take this obliqueness of the equipotential lines, and then on the other side, the equipotential line becomes straight again. You have seen that actually in this graph. Look at this left region here. The equipotential line is vertical here, and then it is slightly oblique somehow, but still, and this is probably here even less inclined. And as you get away from it, after a distance that is basically W, the current pattern doesn't remember that there was a contact, that had some strange boundary conditions. And the same on the other side as well. And so if this long plate here is longer than 2, 3, 4 width, then in the section where we make the measurement, it looks like a very long plate. But if it gets shorter, this is not the case. And so the sensitivity goes down, GI smaller than 1. And actually, there is this technique of conformal mapping that you may not have heard, because the math training doesn't go so far in many curricula nowadays. But this used to be a standard engineering technique for electrical engineers, for mechanical engineers also. It is the mapping of 2D objects, planar objects, by analytic functions, complex functions. Any complex function allows to deform an object into other objects such that the current flow and the equipotential line arrangement in one object corresponds 1-to-1 into those of the deformed object. So, for instance, these current lines in this object here, that I'm just drawing horizontal lines. These horizontal lines represent one grid, one part of a grid. And then we have the equipotential lines. Let me put them now in vertical, just for the sake of simplicity. Those represent another grid. And now under a conformal mapping, this long, infinity long strip of material with contacts in left and right infinity, and two other contacts right here and here can be transformed into the disk, into a unit disk that you see on the right. And infinity is kind of brought here to this point, and the upper boundary here is now this upper boundary here, and this lower boundary here is this lower boundary, and similarly for the other boundaries. And the extended contact that we had here, but very distantly, become point contacts on this. And the equipotential lines that you, or let's say the current lines that you now have, are circles. Yeah, so there are somehow circles that all pass through these contacts, and this is the distribution of the current lines, and the current density is equal to the density of those lines that passes through the sample. And the equipotential lines are other circles that somehow go through this object and pervade the object perpendicularly to the current lines. Yeah, and then we have more and more and more and more, and also I should draw lots and lots and lots of them here, because every line has its correspondence in one and the other object. So that is what conformal mapping is able to do. And so you have a disk with 4 point contacts. You force a current through this point contact into the disk. It flows in this very simple pattern, flows out here, and the equipotential lines are drawn also. And now you can apply a magnetic field, and then the black lines will all be tilted with respect to the blue lines. The blue lines will be unchanged, and the black lines will just be tilted by the Hall angle. And therefore, you will have a Hall voltage between this contact 1 and this contact 2. So one of my PhD students did a lot of conformal mapping because we really wanted to know about these geometry factors and as part of his thesis. Yeah, and so that's interesting. Yeah, point contacts. How do you get a current through a point contact? Yeah, it looks kind of hard because you have an infinity of density of current here. Yeah. And that seems to be hard. Yeah, it looks like you need maybe an infinity of volts to get that current in to drive it, and indeed this is the case. But in the infinitely long plate, you also have an infinity of voltages, 0 volt and then infinity to get anything going, because for every segment you need a certain voltage, and so you have these infinities built in. So this is kind of an abstract thing. The long plate that is infinitely long, corresponding to this abstract disk shape, is something unrealistic, and therefore, as soon as we make the plate long with a given length L corresponding width W, then upon conformal mapping of this object onto the circle, we would have here some finite contacts, finite length contacts. And those finite length contacts make it possible to drive in a current with finite voltages. And as long as the contacts are not too extended, then the distribution of the potential lines in this internal zone is not too much affected by the size of the contacts. And that is the case when the rectangular plate may be 4 or so 10 times longer than wide. Then these contacts are small, and you don't see the intricate potential line shape propagating significantly to the voltage distribution in the center of the plate. When you consider the voltage-related sensitivity, then the conclusion is different. And now we start from the disk. What should the contacts look like so that the voltage-related sensitivity is maximum? And let's assume all contacts to have the same size, and that size is described by an opening angle. You have 4 contacts, You drive in a current from left to right, and then you measure from top to bottom. Yeah? Those contacts have a finite size that can be smaller or larger, but they should all be varying at the same time, alpha, alpha, and alpha. Yeah? And then calculations, the analytical calculations, not the numerical calculations, show that actually for 45 degrees, you obtain the maximum, absolute maximum. Yeah? You cannot be better than 45 degrees within the limits of this geometry. And the geometry factor, G, V, that we have here, that is multiplied by mu h, is 0.47. Now that's some Bessel function of the second kind divided by some other Bessel function of the second kind, and the result is 0.47 approximately. And that's the best you can get. If you make the contact smaller, you will have a smaller number of GV. If you make them larger, you will also have a smaller number of GV. So it's a real maximum. And if you now take this and multiply it with mu h 0.145 or so, then you will obtain 6.8% per Tesla of voltage-related sensitivity. Which means that at 1 Tesla, if you put in 1 volt, you get out 6.8% of 1 volt, 68 millivolt at 1 Tesla. So that gives you immediately an order of magnitude. Now, if you relax this this geometry restriction from 4-fold symmetry to 2-fold symmetry, so only symmetric with respect to reflection, back and forth here, but not rotation under 45 degrees. This has the same symmetries, reflection symmetries, but then also the 90 degree rotation symmetry. So a less symmetric, then you have the option to make these lateral contacts both of the same size, but different from the sense contacts, and then a device with large lateral contacts and small contacts for sensing is the best. And it's better than the symmetric device. It has this number, GV, of 0.76. But you can't get any better than that. If you invent a geometry that is better than this, please tell me. There is, that's an interesting result. Definitely. And the implication is really profound, because you see, this is who makes disc-shaped structures? Nobody. But everyone does squares with contacts either in the center of the sides or in the corners of the sides, or crosses with contacts either on the ends of the branches or in the inner parts, the convex parts of the cross. That is how sensors are designed in reality. Structures with 4-fold symmetry, and each of those structures can be mapped onto a disk by conformal mapping with contacts of same dimensions, of some angle alpha. And we know that 45 degrees is the best. So there must be a dimension of these contacts on this square that corresponds to alpha 45 degrees. And that sensor will have the same sensitivity as the disc-shaped device. It's amazing. These kinds of insights are really useful, because at some point they take you away from you unnecessary dreaming. You think, oh, if I did this and that, and I could be much better, and so now I make this structure complicated. Maybe I let it bulge out something, maybe it's even better. Stop dreaming. It's the same thing as a disk, and the disk of 45 degrees has a maximum sensitivity, and therefore any object of the same symmetry as this disk, with 4-fold symmetry, has the same maximum sensitivity. And you see that the numerical calculations here all peak at at 0.47. Yeah, this is SV, the sensitivity SV, voltage-related sensitivity divided by mu h. This is the geometry factor GV. They all peak at the same value for different values of whatever geometry parameter was taken to parameterize these structures. But for one of those values, you reach the maximum. And if C becomes smaller and smaller, then somehow you're lower, and if it gets larger and larger, then you get also worse. And so you can, for any of these geometries, obtain some maximum of the geometrical parameters to reach that best possible sensitivity. Here is also the fourth one. So this was part of Martin Ponniel's thesis, and the maximum sensitivity is these 6.8% per Tesla. If people start telling you in some conference, I have this device, the voltage-related sensitivity is 20% per Tesla, then you start to be really skeptical. Either they don't have this four-fold symmetry, they have this two-fold symmetry, but if it's more than 11%, there is reason to be very doubtful. Okay, so with that, I will stop, and then we can continue next Monday with these interesting potatoes, or what is it, cucumbers, no, these pumpkins, some decorative pumpkins, to show you some other very general results on magnetic sensors. And I will upload, therefore, tonight or tomorrow, a series, and then we will talk about that on Tuesday. So the course will continue normally on Monday afternoon. And the recording will also be uploaded tonight. So thank you for your attention, and see you next week.